This is a quick lesson on the concept and value of the electron volt in a unit on electrostatics. The electron volt is a convention used to express energies of charges. And you can see the value in here. It's in energy. Notice that it's an energy. It has an equivalency to joules. We know that joules is an energy. And 1 eV is 1.6 times 10 to the negative 19th joules. And if you're keen on constants, you're going to recognize that that is also the elementary charge. 1.6 times 10 to the negative 19th coulombs is the elementary charge. 1 electron volt is 1.6 times 10 to the negative 19th joules. So we're taking this value and taking really small amounts of energy and converting it to a more reasonable number. And that's what it does when we look at really small particles, subatomic particles. They're going to have really small energies, whether it's kinetic energy or potential energy, really small energies. And the convention is to change it to a more manageable number, the electron volt. The definition of an electron volt, and this is if you get asked this anywhere, the definition of an electron volt is the work done to move an electron through a potential difference of 1 volt. And what we know is that the work done is a negative change in potential energy. The change in potential energy is Q times the change in voltage. So when I plug that in there, I get the work from one point to another is the negative of that charge multiplied by the change in voltage. And when I have an electron, the charge is a negative value. So I have negative 1.6 times 10 to the negative 19. That's Q for an electron. And then we're multiplying by 1 volt. And that's where it comes from. You have an electron volt. These energies are so small that the electron volt allows them to be easily expressed. Also, it's convenient in describing the interactions involving the subatomic particles where these energies are multiples of this electric charge. So we would just change this value from 1 electron to 2 electrons or 4 protons, etc. And then you just have the multiple of an electron volt. The examples I've chose are pretty straightforward applications of the electron volt. It says, what is the speed of an electron with 1 electron volt of kinetic energy? And like I said, electron volt is a measure of energy. So we can say that the kinetic energy of the electron after moving through a potential is 1 eV. And I can convert that to joules. 1 eV is 1.6 times 10 to the negative 19th joules. So that's how much energy that electron would have. We also know that the kinetic energy of any particle is 1/2 mv squared. If I wanted to solve for the speed, I would multiply by 2 on both sides and divide by m, take the square root, so I get 2 times the kinetic energy divided by the mass of that object. In the case of an electron, I can plug in what I know. I'm going to have 2 times the kinetic energy, which we know is 1.6 times 10 to the negative 19th joules. When you use this equation, you have to use joules in here. You cannot use EVs. I'm going to divide by the mass in kilograms, so that for an electron, if you don't know off the top of your head, it's 9.1094 times 10 to the negative 31st kilograms. And then I'm going to remember to take the square root of that. And when I run this through the calculator, after 1 eV of kinetic energy, we get 592,693 meters per second, which I approximated to be 600 kilometers per second, which is a pretty good clip. That's pretty fast. I mean, it's not the fastest for an electron. Electrons go much faster than this, but it is pretty fast. It's 1 electron volt. So I ask you to compare it. How fast would you need to be moving to have this same kinetic energy of the electron? For an electron moving at 600 kilometers per second, that kinetic energy, how fast would you need to be moving to have that much kinetic energy? So we have the equation already. I already solved. We know that 2 times the same amount of kinetic energy, well, 1.6 times 10 to the negative 19th joules, same amount of energy, but you have a different mass. And I just chose like the mass of an average human being on the planet is around 70 kilograms. And we'll remember to take the square root of that. And when you run this through your calculator, you get a super small number, 6.67 times 10 to the negative 11th meters per second. It seems like you barely budge one direction, and you're going to have the same amount of kinetic energy as an electron moving at 600 kilometers per second.